Hello everyone. This is the third session of SVR 2021. This session is dedicated to deal with tracking and pose estimation. We have 4 papers, about 15 minutes each paper. There will be a video presentation, 7 minutes of video presentation, followed by a 7 minutes of questions and answers to all the presenters, to the presenter. You can pose your question at the YouTube or at the Discord, and we'll give your question to the presenter, okay? We start with the first paper by David. So let's start with the first video of David.
Hello and welcome to my presentation. I am David Scherfgen from Hanover University of Applied Sciences and Arts in Hanover, Germany. I will now briefly present the paper that my colleague Jonas Schild wrote together with me, which has the title Estimating the Pose of a Medical Mannequin for Haptic Augmentation of a Virtual Patient in Mixed Reality Training. In a previous research project, we've been developing an application for emergency paramedic training, and also we've been testing it in practice with our partner schools. This was a pure VR application. Only HMDs and controllers were used. In classic non-virtual training, trainees practice on medical mannequins, also called patient simulators. We thought it would be a good idea to make use of these mannequins in the VR training too, and so for our current project, we set ourselves the goal to bring these mannequins into the simulation as haptic proxy objects. That means that trainees can now touch the virtual patient, but in reality they touch the mannequin. The reason to do this is to potentially improve presence and realism of the training and possibly make it more effective. How can we use a medical mannequin as a haptic proxy? On one side we have the mannequin in the real world, and on the other side we have the virtual patient in the virtual world. For the mannequin to become a haptic proxy for the virtual patient, their positions and body poses have to match in both worlds. In other words, we have to detect the mannequin's pose, which consists of its position and orientation in 3D space, and also the rotation angles of all its movable joints. Once we have determined that pose, we can apply it to the virtual patient. In the ideal case, they match perfectly, and whenever the user touches the virtual patient with their virtual hands, they also touch the real mannequin with their real hands. From our previous experiences, we learned that if we want to integrate such a system into practical training, we need to make it as simple as possible. That also means, ideally, we would require 0 additional hardware, so no extra Kinect or other sensors. After considering various options, we decided to take an image-based approach. Using the cameras that are already built into our HMDs, we take images of the mannequin from different perspectives. We feed these images into a body key point detector. We use OpenPose for that, which applies a convolutional neural network to find the 2D image coordinates of up to 25 different key points of the human body. And then, from the key point coordinates, we compute the mannequin's pose. The coordinates of the detected key points in the camera images are 2-dimensional. But for our first step, we need 3D positions of the key points. In order to get these, we use triangulation. For that to work, we need to know where the cameras are located and how they are oriented in space. In our case, since the cameras are mounted to the HMD, we can use the HMD's tracking system, like SteamVR, to get that information. And we also need to calibrate the cameras, find out their optical properties, and also where exactly they are mounted on the HMD, and the time delay with which we receive the camera images. For the actual pose estimation, we first need to annotate the 3D model of our virtual patient this has to be done only once. For every key point supported by the key point detector, like the 25 key points from OpenPose, we need to place a dummy object inside the virtual patient's bone hierarchy or skeleton at the appropriate location. We also must look at all the mechanical joints of the mannequin and examine their physical properties, their degrees of freedom, which means how far they can be rotated in different directions. Then, at runtime, using the triangulated 3D key points of the mannequin, we first roughly estimate the mannequin's overall position and orientation. We do that by leaving the 3D model in a fixed, neutral pose, like in the image, and find a translation and orientation that align the mannequin's 3D key points with the 3D key points that we place within the virtual patient's 3D model. That initial estimate is then refined using nonlinear optimization, where we minimize the reprojection errors of all the observed key points in all camera images. During optimization, the joint angle limits act as constraints to the solution in order to prevent impossible poses. Now let me say a few words about the system's performance. We haven't done a full evaluation yet, but we typically achieve an error between the real mannequin and the virtual patient of about 4 centimeters, measured at key point locations. We suspect that this is caused to a significant degree by mismatches between the mannequins and the patient's body proportions and shapes. If the lengths of the limbs don't match well, then there is no good solution consisting of only bone rotations. These results are not good enough yet for precise medical interactions, but we think they are sufficient for some social interactions, like touching the patient's shoulder to give comfort. The system is not yet real-time capable, because we need at least 5 to 10 camera images from different perspectives to get stable results, and processing a single image takes about half a second. We're already working on a user study that will investigate whether a virtual patient that can be touched actually increases presence and realism. We'll also keep working on our 3D model to make it more similar to our mannequin. That's a balancing act, because the mannequin looks quite unnatural, and we want the virtual patient to look realistic. Finally, we might also try to specialize the key point detector by training it on images showing only medical mannequins. That concludes my presentation. I thank you for your attention, and of course, for more details, please have a look at the paper. Thank you.
Okay, thank you very much, David. We can see David now. Where is David? Hello.
Hi.
We have some questions already at the chat, but I will ask first a very technical question. You're using OpenPose.
Yes.
Have you considered MediaPipe, YOLO, or any other RGB camera solution? And does any of these alternatives give you a 3D point?
Can you repeat, please, what kind of libraries we have considered?
MediaPipe, YOLO. There are other similar solutions to OpenPose. Do you know
Okay. So all of these work with color images, right?
Yes, RGB camera,
So
2D camera.
So they would not immediately give me a 3D position, right? Of course, since we are working with the Valve Index HMD, this has a stereo camera. So we can make use of that and run the key point detector on both images to get a rough estimate of the depth of each point, right? Of course, this is not very precise because of the rather small baseline. You had a second question, right?
Okay, and well, I've asked that because MediaPipe, I suppose it can give you 3D 3D information. and that's that. I'm not sure how precise they are, but I think you can take with one camera, not a stereo camera, one single camera, 2D camera, and RGB camera. I think you can estimate with a little bit of fairness the 3D point. But you've answered already my question. There is another question here at the chat, which is how does the user interact with the real mannequin since her hands are occupied holding the controls?
That's a good question. If that's a problem for the original Vive controllers that we all know, because with these controllers you really have to use your entire hand. But the Valve Index comes with some better controllers, which allow you to stick your fingers through the controller to touch some real objects. So your controller is held in your hand using a rubber strap, and you can use your fingers to manipulate some buttons, but you can also reach through the controller and physically interact with objects. We
Could you
also
give us?
considered hand tracking, but the products that we tested did not really convince us, and we didn't want to add any more additional hardware complexity, because the people that are actually eventually going to use this, they are like medical emergency trainers. They are not computer scientists. They don't typically have a technical background, and it's already quite a lot of work to set up a VR system without hand tracking.
Yeah, and there is another point that I would like to make because I suppose MediaPipe can track 2 or 3 bodies at the same, actually many bodies at the same time, and their hands, their limbs, and so on. So with you might be able to track both the user's hand and the mannequin whole body with the same camera and the same framework. But
Okay.
I'm just saying. I suppose I'm not sure about that, but I think it's worth trying. It's worth
Yeah.
investigating. Okay.
Thanks for pointing that out. Yes.
Okay. I was just 1 minute extra. I was wondering. You said that you're planning to give people the opportunity to experience a real setup, the real emergency setup. But how do you plan to get the feeling of emergency? Blood everybody everywhere, and tension, things like that.
So the so our project is actually in use already in a testing campaign, so to say, and the concrete scenario that we are now doing is a burn injury. So a patient with heavy burning wounds has to be treated, and you will actually be able to talk to him a bit at least, and he will scream and make sounds of heavy pain, and that's already enough to stress people. Even if you don't have this, we have observed that the people who are using the system, they really get immersed quite a lot, and they feel almost the same stress as in a real scenario.
Excellent. Okay, thank you very much. We're going to the second paper. David, I hope you have success in your project. Let's go to the second presentation. Biomechanics sensor nodes for body tracking, a development solution for virtual reality interaction. Let's see the second video.
Hi everyone, my name is Elvis Ribeiro and I'm going to present the paper Biomechanics Sensor Nodes for Body Tracking. a development solution for virtual reality interaction. This presentation is divided by introduction, the presentation of the BSN asset, the applications we made using it, and the conclusion. Virtual reality is increasingly present in the healthcare area. It has been used in many ways, for example, as a motivational tool to engage patients in the treatment, a training environment for the health professionals, and to collect and analysis of patient data during treatment sessions. However, despite the immersion has been quite easy done recently, the interaction becomes to be a challenging task because it is either expensive to implement using proprietary solutions, or it's hard to implement using Kinect or sonar devices. So the Brain Institute made the biomechanics sensor node, BSN, which is a wearable device equipped with a 9-axis IMU sensors, which communicates through Bluetooth Low Energy, with the advantage of being low cost. So we wanted to make a plug-and-play asset for Unity, which would be easy to add in any project existent, being portable to Android and iOS, and now allowing us to connect multiple devices simultaneously, having a friendly graphical user interface, and allowing the user to configure the application remotely. This part is important, where the patient is immersed in the virtual world using the smartphone, which the BSNs will be connected. So it makes hard to the professional to configure the application with the same smartphone. So with this asset, it is possible to the professional configure the BSN connections remotely. To achieve that, we chose this architecture, model view controller, which will modularize the asset, allowing us to distribute the application by two devices, making the application may or not be remote. So the model is responsible for all the Bluetooth communication and the mapping of which device controls which object in the scene. The controller is responsible for getting the commands from net and application to the model. The view is composed by mainly the interface of the application and the configuration client, which sends commands to the model. So this is the interface of the application. In it is possible to search for the BSNs, connect to each one of them, and configure which BSN will control what part of the body in the scene, or object, or any movable game object in the Unity. So we made these applications using the BSN. The first one is the E-Street, is a virtual city where the user equipped with BSN in his legs can walk through the city. And the second one is the puzzle brain. It is a puzzle where the user controls a virtual hand which rotates the pieces, trying to make the picture right. Low streaming rate of data from the BSN, about 15 Hz. making it impossible to calculate the displacement of the device, which takes us to calculate an integral, and the low rate of data makes the input of a lot of noises in the integral, and the Android limitations, which limits the connection from only 7 BSNs, which difficulties the tracking of the whole body of the user. For future works, we pretend to extend the application to new platforms, especially Windows. Therefore, we think that using more than one Bluetooth dongles, we could connect to more BSNs and divide the connections by the two BLE dongles. And we pretend to make some firmware enhancements in the BSN firmware, possible to increase the streaming rate. Thanks. Questions?
Okay. Thank you very much, Elvis. We have some questions already. Let me start with one of them. The question comes from Professor João Marcelo. How is the total cost of the solution presented in the paper? And I will add, BSN might be a commercial solution, right? How does it cost a BSN? How does it cost to produce your own IMU unit, for instance? Do you have this idea of costs?
Good afternoon, Marcelo. Good afternoon for all of you watching my presentation. The cost of one single BSN is about $50. At the time it was produced, I don't know how is the market today. And yes, it is a market solution. It can be sold, and since the professional can use any Android or iOS device, only the cost of constructing a BSN is counted.
Okay. And the second part of João Marcelo's question is, how does it compare to other tracking systems, such as image-based, like the one we've seen in the previous paper? And what can you say the difference between those kinds of solutions, a physical sensor and image-based recognition style?
The main thing is the BSN solution does not suffer from obstacles in front of the camera. So you do not have to be in front of the camera to track the movimentation.
Mm-hmm. Okay, that's the occlusion problem we face in most of the tracking systems. But what can you say about accuracy, about number of joints? I can imagine, like, if I'm not mistaken, OpenPose MediaPipe can track up to 31 different joints. If you try to track 31 joints with BSN, how it would be a person wearing all the beacons everywhere? What would you say?
About the drift, yes, the BSN suffers from drift, mainly because it is only a prototype. We pretend to enhance the accuracy of the BSN in the future works, And because of the limitations of Android, we can only connect 7 BSNs to a single Android device. So in the next paper, we pretend to implement a solution for Raspberry Pi, so we can use more USB Bluetooth dongles, so we can connect more than 7 BSNs. So yes, the user would wear all of them in each body part.
Okay, is it adjustable for wrist or thighs, for instance, or any other part of the body? How do you adjust the placement of each BSN? There is a adjustable strap, or how does it work?
Yes, it has an adjustable strap using elastic. So
Right.
yes,
Okay. But is it comfortable?
yes,
Yeah.
yes.
Okay.
I've tested.
Did you? Excellent. Very good. Thank you very much, Elvis. Let's go to the third paper. The third paper is the virtual Kinect. Let's see the third video.
Hi everyone, my name is Thiago Lafayette. I came here to present a paper entitled Virtual Connect, a tool for human movement analysis. Biomechanical analysis has many applications in sports, rehabilitation, and healthcare in general. It's used the standard set by International Biomechanical Society (ESB) as anatomic reference and joint placement. For this, it's necessary to transform the movement data into computational data, and for this, the Movement Capture System (MoCaps) is used. Among the extant methods, the optical system works with infrared cameras or common cameras, and also mix of both, the RGBD cameras. The right picture represents a schematic of how an infrared reflective marker system works, and the medium picture is an example of this application for a gait analysis of a child. Among the methods of optical system, the Connectivity can be highlighted because it's a low-cost RGBD system, has no markers, and an open SDK, capable of tracking people's joints in real time. Additionally, the literature reports its application in specific cases for biomechanical analysis. However, it was discontinued by Microsoft in 2017. In addition, the successful release of Kinect Azure has restriction on this pursuit to the location unavailable for the United States and China. Plus, the health restriction because of COVID-19 pandemic changed the way we do research and share equipment, thus making it difficult to use and obtain connectivity in general. In parallel, the emergence of methods that use only RGB cameras such as webcams for pose estimation has made it possible to create more analysis tools, as it drastically reduces the cost of equipment. Therefore, the problem is the difficult to access connectivity and the need for the continuing of the research that use these methods, aggravated by the lack of equipment and the social distance. In order to solve this problem, this paper aims to use a RGB camera method to simulate the presence of connectivity for applications already developed. To this end, the paper has two main objectives. Primary, to allow research and use Kinect to continue projects with the same code, just by changing the DLL. Secondary, to compare the joint tracking of the media pipe with the Kinect. For this work, Google Media Pipe was chosen as RGB capture method. MediaPipe was released in 2019. Its tool BlazePose is able to recognize different 33 joints and reference points. This image is a skeleton generated by it. Of these reference points, 11 are located on the face and the rest are joints. Then, for MediaPipe is born the Virtual Connect (VK), using API to provide joint information that is supposed to be captured by Connect-V2. This requires memory sharing from MediaPipe runs in Python to the C++ Kinect SDK. Using 640 by 418 image as input, it's possible to transfer the joint information to the application that wants to work with the Kinect from the MediaPipe tracking. The image on the left is the Virtual Kinect initialization and identify the points and sharing the memory for the applications with Kinect. On the right side, the image is the implementation of the packet retrieval in C++ in the application that is supposed to be running the SDK. Since the two methods have different representations of the skeleton, as such be seen in the screen, Media pipe has a high total number of landmarks, although Kinect V2 has some extra joints, such as tools located in the spine. Then it was necessary to determine its correlation are direct and which correlation needs to be approximated. The approximate correlations are highlighted in the image, being the trunk and the hand regions. Thus comes the estimation of the skeleton and how it will be represented by the virtual Kinect. This table expresses all the approximation correlations used. A total of 8 joints had to be correlated indirectly using arithmetic average of the reference points. The approximate points are front spine, spine base, spine mid, spine shoulder and neck, and from hands, the hands and the hands tip. The test performed in this paper consists in the analysis of a video file extracted from the Kinect Studio recording. The video contains a left shoulder abduction, a total of 21 landmarks are captured, from which the 2D position of the joints generated from Virtual Kinect was analyzed, overlapping the Virtual Kinect skeleton and the Kinect skeleton. The table in question showed the result of its analysis comparing the 21 joints captured from the Virtual Kinect. So let's take a closer look at some landmarkers. First, tools generated for indirect correlation and tools present in the execution of the movement. From the highlighted landmarkers, the neck and the shoulder had the lowest variation results. The spine and base, on the other hand, had greater divergences, although the relationship is the same as for the spine shoulder. This divergence occurs mainly in the wide position, coming from the position of this point by the Kinect V2, since it's positioned higher than the middle point of the hip. As well, spine mid had also a large wide shift, due to the approximation of the center of the quadrilateral formed by the hips and the shoulder points. Each in the Kinect is not centralized point. Now, the point under observation from the arms. The left arm shows a great variation of these markers, shoulder and elbow, compared to the right, because it is the mobile segment of the recording. This indicates a dynamic sensibility between the methods, so it's necessary to determine which one is more sensitive to the movement. However, it was possible to obtain from the recording all the reference points. Only some numerical adjustments are necessary for the correct overlap of the skeletons. It was noticed that some landmarks are lost throughout the recordings, because the Kinect works best with the body fully present within the records area. In the recording question, it didn't feature the presence of the feet. It loses some of its reference for lower limbs, as can be seen in the right image, where the red-white dot represents the Kinect's knee estimate in the middle of the thigh. It can be concluded that a method using only RGB files can generate 2D data similar to Kinect V2, using an ordinary camera as a source. Also, numeric adjustments can provide a better skeleton overlay. The DLL developer allows the programmer to update the original code without the need for significant adjustments to the VK's usage. In closing, it's worth noting that the projects are open source to be made available to the scientific community. Thank you very much for your attention.
Okay. Very good, Thiago. Thank you very much. Excellent presentation. People are concerned with 3D information from these image-based tracking system. What can you say about 3D accuracy? How to compose a 3D information from 2D image? What can you say about that?
Now the software uses directly the 3D information that MediaPipes can provide. So actually we will try to compare with the Kinect that is a RGB camera and has a absolute reference different from MediaPipe that use the center of the ribs to estimate this 3D information. So now we are working that and we evaluate the difference between these two, and also we'll use physiotherapists professionals evaluations to make that comparison of the tracking movement. Is actually right circle with the real movement.
Okay, but let me stick with this question for a little bit longer. This is a question from Julia Tanus from the YouTube. But what I'm trying to dwell on a little bit further is why media pipe? What are the main difference between media pipe and open pose? For instance, the first paper used open pose,
Uh,
YOLO, and other
One of the
2D.
reasons is because the meta pipe is new. It's
Mm,
actually the, as I said in the presentation, he used the Blaze Pose to get that information. And Blaze Pose was released in 2019, so it's really really recent. So is there is not some different, there's not so much solutions with that, and start working with MetaPipe is a good start. And actually a new light that in research that can use that tool or not. So it's one of the reasons that we use that. And it's completely open, and it's actually a really really reason that we chose that.
okay, got it. Okay, there's a question from David Scherfgen, the first presenter from the first paper. The question is, have you tested this with some existing software, maybe even a game, or are there other aspects of the Kinect SDK that you haven't
Uh,
faked yet?
the main solution actually we are trying to use is used with our rehabilitation software that use Kinect as well. So we're gonna use the Visual Kinect to simulate into a MIR rehabilitation. That's a rehabilitation software for use in opera, uh, in arms rehabilitation. It's in has a really game thing. It's actually not a game, but use gamification in his application.
But is it a commercials game or is
No, it's not a commercial
home?
game. It's
Mhm.
rehabilitation software
Mhm.
made from Voxer, and it's not a commercial.
Okay, got it. Let me think about. You said Kinect V2 was not a good success, right? But Kinect V1 was, right? So, have you considered, the group has considered to include Kinect V1 as one of the um, alternatives in terms of using MediaPipe to emulate V1, using MediaPipe to emulate V2?
Actually, not, because the V1 and V2 has a very different quality of tracking. V2 when it was released, he's a better tracking because it changed it from struct light to time of flight, and just this get him a better accuracy, and he it has more joints. So it's not good actually option to go back to V1, since you have the V2, it's already better.
Yeah, but I brought this question because you can still find Kinect V1 to be sold in the marketplace, but you haven't had the opportunity to buy Kinect V2, right? So people have some games, some application using Kinect V1. So I suppose you would have a more interesting person, customers or partners, whatever, if you have also included Kinect V1 as one of the alternatives for the system. Do you think it's interesting?
Yeah, this can be it's a future work to add the V1. Actually, now we are focusing and compare the media pipe and V2, and actually the LEL is not change a lot. Is one of work for the same flow. The project now is open source and is available in the GitHub, so everyone can just see that. It's the link there is in the paper, and the idea that is the same as MetaPipe. Just MetaPipe is continue update his frameworks. The Visual Kinect is gonna try to update itself with the angle analysis and something like this, because the objective is make just not available the research tools the connectivity tool if there is him in the there's not it in the moment, but try to figure out how MetaPipes works in the pose estimation and in movement analysis. Is this two men of the work, and you're trying to make this in parallel and to create more tools to the community.
Um, Thiago, between ourselves, imagine no one is listening. Okay,
Okay.
what can you say about the future of uh, pose tracking, gesture tracking, either using image-based solutions or device-based solution? Just between us, okay?
Okay, I'm not in the chat right now. I'm
Yeah.
not the chat. It's just friends talking. I think that the future is gonna be just RGB cameras because they are easier, they are smaller in most aspects and cheaper, and actually it's easier to use to implement and something like every cell phone has RGB camera, so it's actually more accessible. So why we have think that well we now create a new equipment to work to develop itself, just we can just use what it has right now. And I think that connected and Astra and something like this is was great, amazing. But RGB solutions is gonna develop faster and gonna be actually better in the future.
Thank you very much. You see, you just brought for yourself a very good argument, and you have the fight with the second presenter with Elvis. So thanks, we're on a remote mode. We're in different locations, but I think we have to think about all the implications, the accuracy, latency, applications for all these kind of solutions. They all have their places. They all have their own problems. But
Of course.
I think for the time being, image-based tracking seems to be more useful at the moment.
Nowadays it's not is we're not in the future. So actually yes, there is problems, and this problem is going to be better because when more we resolve that, more we're going to increase and develop. So it's good to have problem. It's not bad.
Okay. Thank you very much, Thiago.
Thank you.
Congratulations. Very good. Let's go to the fourth and last presentation, last video from this session.
Hello and good day. My name is Gabriel Sierra and I, along with Carlos Rocha and Wilson Sarmiento from Universidad Militar Nueva Granada, bring you the following proposal. Non-traditional rig for virtual environment systems. Case study ARM rig. We would like to thank the SVR 2021 for this opportunity. First, I'll talk about our motivation for this work, as well as some background of related works. Then, I'll talk about our approach to the problem and the methods we use to test it, and finally, our conclusions and future considerations. The skeleton rig has been a traditional approach to character animation and tracking. In some cases, traditional skeleton rigs generate undesirable deformations of the 3D mesh. One of the most popular issues is the candy wrapper effect. Depending on the final purpose or target platform of the character, the rig will have different requirements and limitations. Some approaches generate suitable results in 3D animation for audiovisual production. However, despite how useful an automatic system can be, there is always the need for input from the 3D artist. For real-time tracking, some approaches are focused on improving inverse kinematics, tracking correction, or imitating muscular deformation, but these solutions require robust algorithms and can be very resource-intensive. In the state-of-the-art and industry, There are many non-traditional skeleton rigs, but these have not been evaluated to improve candy wrapper problems in virtual environments. We propose using a non-traditional rig that includes an extra joint between the middle of the wrist and the elbow joint to get the best skin deformation results when the wrist rotates while following a tracking system. The new joint's rotation is to be exactly one half of the wrist joint's rotation, and it has certain limitations at extreme angles, but it looks much more natural than the classic skeleton arm of only elbow and wrist joint. Restrictions of the COVID-19 pandemic prevented us from doing a new experiment with users, so a subjective test with experts was performed using pre-recorded data of a previous experiment done with users. In this previous experiment, the users did an interactive task inspired by the classic toy of fitting blocks inside a template hole. The user must then grab each block with their hand and place it inside of the box, located at the center of the screen. A leap motion sensor was used to capture the movement of the user's fingers, hand and elbow positions, and rotations, with a frequency of 10 Hz. All data of 20 different users was recorded in plain text log files. All log files are then analyzed to identify 6 motion tracking sequences, where the candy wrapper problems in the wrist of the user avatar were more prominent. The non-traditional rig and the classic rig were both applied to a freely available model made with the software MakeHuman, using a geodesic voxel bind, and then exported to Unity. A viewport camera was placed so that both our models would be centered in the same place in each shot. The setup replicates the original position of the user's viewpoint. 6 videos, one for each motion track sequence, and so that 8 experts could observe the difference each rig made on different movement sets, in shaded view and then both in wireframe view. The experts had wide experience in 3D modeling, 3D animation, and character rigging. For each video, experts were asked to fill a form composed of 2 questions. To eliminate possible biases, in 3 videos the non-traditional rig is on the left and in the others on the right. This table shows the results of question 1. The last column is the mean of how much each clip was liked, which was, coincidentally, 1.6 for all videos. It is possible to assert that experts observed relevant differences between both skeleton rigs. Now this table shows the results of question number 2. It is possible to observe that the majority of the experts agree that non-traditional rig allows the model to have a more natural look when it deforms the mesh when the wrist twists, closer to what they would expect to see in real life with their own arms, in contrast with the classic rig. Using a non-traditional rig in a virtual environment is a suitable solution for candy wrapper problems in avatar limbs while tracking user movement. The results of the experts' subjective validation are promising and show that most of them prefer the non-traditional rig in terms of naturalness across all tests. This is a work in progress, however. Further work will be to test this approach with experiments with users. This work only focused on the hand-forearm area. Further work will also be oriented to test other limb articulations. Again, we would like to thank the SVR 2021 for this opportunity. If there are any questions, please go ahead. Thank you for your time.
Okay, thank you very much, Gabriel.
Hello, good
Very
afternoon.
interesting um, work. Rigging is a very important problem for animation, for virtual humans, for a lot of different computer graphics application. So it's nice to see some work done in such an interesting and visually impacting area. I would like to ask you. I just want to get a feeling of what happens when you have your solution and the traditional solution. What do you see? You said it looks much more natural. What is more natural? Can you describe a little bit more, please?
Sure. With a traditional rig, when you twist the arm, when you twist the arm, you can see the candy wrapper effect relatively sooner than with our method. With our method, the skin deforms a bit more natural, like more smooth. It doesn't twist so hard at the wrist.
Mm. And okay, I
Mhm.
got it. Do you what other parts of the body do you think this extra joint could help on this kind of deformation?
Yes, even though our research was only focused on the wrist and forearm area, we also experimented a bit with the upper arm area and noticed that between the shoulder and the elbow, the same thing also applies to a certain extent, but we left it for further experimentation later on.
There's a question from David Sherfkin. He asked, "Do you think you can solve all similar problems by adding an additional joint like you did for the arm? I suppose for the neck, for legs. Is it as a um, standard solution? You just add another joint in all these limbs, for instance. What do you
Well,
think?
at least for the shoulder and elbow section, I think it should work fine. For the rest of the body, I'm not really sure.
Mhm. If you consider everybody to use another joint in the middle of your arm, you actually um, um, giving people another skeleton model, right? There
Mhm.
are so many models already. So yours will be just another one. Instead of 31 joints like media pipe, you have what? 40, 45 joints. How would you convince people to use your model, your rigging model?
Well, I think immersion is very important. In some of the extra research we did, how immersed somebody is in the virtual experience heavily impacts how they feel while inside the simulation. So I think in the future it's going to be very important to make it feel as real as possible so people can feel very comfortable in whatever they're doing, be it a game or interacting with other people. It makes it feel more immersive, more real.
Have you any idea on how's the computing overhead for every single point? And is that it's time consuming, or it you know just a little bit of extra time to take in for handling the actual tissue?
You mean resource based?
In terms of computing power,
Well,
does
it
it take longer
shouldn't.
to how longer it will take it to calculate the formations and so on?
No, it shouldn't make a very noticeable difference. It's a simple dividing the angle in two, and it
Mhm.
shouldn't be a problem. The tracking
Okay.
is simply the wrist, so no problem there either.
Hey, thank you very much. Very interesting. So you're using lip motion for for controlling and for tracking the hand, and then you calculate back the position of the arm. Is that right?
Exactly, with inverse kinematics and
Okay.
yeah.
Okay. But there's no actual difference in terms of forward kinematics if you have a robot or you producing an animation, it will work the same, I suppose.
Mhm.
Okay. Okay, very, very interesting. Congratulations.
Thank you.
We reached the end of our session. I think all the authors very, very interesting solutions, very promising ideas, and I invite everybody to keep using YouTube and Discord for communicating with us. And I hope you see in the next section. Thank you very much. All the best.